States. It serves, as I said, Pennsylvania, New Jersey, Maryland, Kentucky, parts of Ohio and Michigan, and I think it even extends out perhaps into portions of Minnesota. It roughly serves about 60 million people, has roughly 199,000 megawatts of generation represented, in there.
I'd ask now if you could describe the equipment that comprises an electric power generation plant of this type. And it might be just most convenient for all if we were to turn to Exhibit A8 and have you describe that exhibit. So that's for everybody up here, A8.
So Exhibit 8 is a drawing showing the general arrangement of the site. And you see a number of components on this drawing, starting from left to right. You see a series of items that are lined up. There's 3 identical items. Those are the combustion turbines. They're labeled as item number 1. They are connected to the boiler or the heat recovery steam generator. That's item number 2. And they are arranged in series so that the piping, the steam piping from the boilers can all be connected together and then sent, marshaled together and then sent over to the steam turbine.
Mr. Nally, if I could interrupt for just a second. And I know you described this generally earlier in your testimony, but for many people, I think technology is not well known. And so as you work through your description of each of the individual components, if you could also describe their function and purpose.
Sure. Yeah, so, the combustion turbine is, really, I think the best way to describe it is, if you were to have a pinwheel, right? And you're a kid, you had a pinwheel and you blew on it and it spun. What the combustion turbine is doing is basically that. And we're trying to, convert this rotational motion so that it will drive a generator. So the combustion turbine really has 3 parts to it. It has a compressor section, and it has a combustor, and then it has a power turbine. It's really, sort of the same features that you would have in your car. You need to have air, you need to have fuel, and you need to have compression. The same things are happening here. So the way it works is that the turbine spins, it takes the air in and it compresses it up to about 500, maybe 600 psi, and from there it goes into a series of combustors. For these machines, these combustors, they're about this big. They look like cans, and I think there's about 12 of them arranged in a circle around the machine, and these are actually very complex pieces of equipment that include proprietary technology, from GE in this case. There, the fuel is injected and it combusts. And so now you have a stream of hot gas that's probably 2,000 plus degrees F, and that expands out over the power turbine. Now the pinwheel is working in reverse. The power turbine is not only driving the compressor, but it's also driving the generator, and about 1/3 of the power from that power turbine is driving the compressor. The other 2/3 are driving the generator. So you're generating power there. That, after it comes out of the power turbine portion, the temperature has dropped to about 1,200 degrees F or thereabouts, and there it's passed through a boiler, and the boiler basically just looks like a radiator with a bunch of sheets of fins with thin tube on it, and water is circulating through these tubes, going up to drums, and it's being heated in a fashion such that the water that's flowing through there is ultimately turned to steam, and then that steam comes out at about 1100 degrees F, 2400 psi, thereabouts. That steam is sent to a steam turbine where the same process happens again. That steam expands through a steam turbine, the pinwheel action, turn a generator, and that's how it works. The steam from the steam turbine is then exhausted from that steam turbine, sent to a condenser where that heat has to be removed so that you can condense the remaining steam, and that's what the condenser and then the cooling tower is. One thing I wanted to mention here is, this figure shows a cooling tower. This is the wet tower. This is something that folks, it uses quite a bit of water. There's been a number of discussions that we've had, not only with you folks, but with folks in and around, Jessup, who are concerned about the amount of water that the plant consumes. We've also had discussions with the Susquehanna River Basin, who recently, back in the beginning of March, they issued a position paper, if you will, about their desire to see power generating units use air-cooled technology. And so, we actually have been, looking at this, and we're ready to, we've made a decision to change the technology on this facility to go from a wet tower to what we call a dry tower or an air-cooled condenser. So what that means is that the water consumption that the plant would have otherwise had for cooling, that consumption goes away, and that the overall plant consumption of water is going to be substantially reduced.
So how will that change this site plan?
The site plan will, this is a decision really that we just made. So the site plan is going to have to be modified to include the air-cooled condenser.
As you look at the plan, are there other significant features that you haven't discussed that you'd like to draw to the attention of the council members?
Yes, there are several. Item number 5 that's listed here, it's a large rectangular area. That is the switch yard. That is where the power output from the 3 combustion turbines and the steam turbine is being able to be sent into the grid. Basically how that happens is each generator, and there's 4 generators here, has output that goes through what we call a step-up transformer, where the output of the generator, which is typically about 18 kV, would be stepped up to 345 kV. And then, those 4 step-up transformers, the output from those 4 transformers will be, connected by wire over to the switch yard, where they'll be, attached to a bus, and then the bus will be connected to a series of switches that will help get that out into the grid. The other item that is here is that we have the item number 11 and 12 is the gas metering station. This is where the plant connects into the gas transmission system. And item number 12 is a gas compressor. And the reason we need a gas compressor because for the most part, the gas may have adequate pressure, but there may be periods of time where we need to get the gas pressure high enough so that it can be put into the combustion turbine. So we step up that pressure in order to do that. And then there are other buildings here that include demineralized water treatment. Because the water we use, in the plant and in the steam system has to be very pure, we have to demineralize it, and and that water is constantly recycled within the cycle. So we produce a small stream of demineralized water to make up to the system. We always let a little bit of water down, so there is a small amount of makeup about 1% of the steam flow that's constantly going on there. There are other systems that are included in here. Some various gases. We use carbon dioxide for fire suppression. There's a hydrogen system here that is used for cooling the generators themselves. So all of these things comprise the plant. We have water storage tanks.
I noticed that the table on the right side of this site arrangement plan includes references to height of buildings. Can you identify the buildings that exceed 70 feet in height?
Yeah, we've included the approximate dimensions of the various pieces of equipment, the length and the width and the height. I think of note here is that the boiler or the heat recovery steam generator has a height of about 115 feet, and the steam turbine building has a height of about 100 feet. And in this depiction, the cooling tower has a height of about 95 feet. The air-cooled condenser would actually be a little bit higher than that. The rationale behind the height of these things is that the steam turbine building, for example, the steam turbine itself has to actually sit up on top of a pedestal, and because the way the steam flows into it, they call it a down exhaust. It actually, the exhaust comes out of the steam turbine and then flows down, so it sits on top of the condenser. In the case of the air-cooled unit, what will happen is it will sit on top of, essentially a large duct that will duct that steam over to the air-cooled condenser. The steam turbine still needs to sit up, fairly high, and the height of the steam turbine building is set by how high that steam turbine needs to sit and how much space you need above the steam turbine, so that there's a crane overhead that can pick up pieces and move it off and do maintenance on it. And then there's room above the crane just to, keeping it under a roof, and that's really what drives the height of that. The heat recovery steam generator height is essentially driven by the height that you need to have for the steam drums. And what the steam drums are is, when you're trying to, create steam here, you get to the point where the water is almost ready to boil, and you do this in stages of pressure. So you have a feed water pump sitting right there, and you need the feed water pump to be able to have some positive, pressure on the suction side. So one way to do that is you raise the drum up, so there's a column of water sitting on top of the feed water pump suction, and that height elevation helps keep what we call a net positive suction head on the feed pump suction. Otherwise, the water at that point is really so hot that if you drop that pressure anymore, that water will flash to steam and you can probably destroy the pump. So, that's the mechanics, if you will, of what's happening at that location. And then, the cooling tower or the air-cooled condenser, in this case, what's going to set the height of that is that what you essentially have is a radiator that's sitting up in the air that has a number of cells. Each one of these cells will have a fan that blows air, across these radiators that are set in sort of like almost a teepee type configuration. Steam comes in the top, it sort of goes down the side, and air is blowing up and through, and then by the time it gets down to the bottom, it's condensed. You really need enough room in order to get all the air in underneath there, and so you can get the center cell so that the proper airflow is occurring, and that's really what drives that.
If I could ask Mr. Nyman if you could turn to tab 9 in the binder, so exhibit A9, and describe what we have there.
This is what you're looking at is a 3D rendering. This is a computer rendering of the project. And, you can see three structures that are lined up. You see what look like big rectangular areas lined up sequentially. Those big squares that are sitting somewhat vertically are the air intakes to the combustion turbine. Just behind that is the combustion turbine itself. And then the exhaust is going into the boiler, and then you see that thing that has a bunch of ribs on it that's connected to the stack. That's the boiler, and you can see on top of the boiler there are some large, what look like diameter pipes. Those are the drums that I was referring to earlier. The piping that comes off of that is connected via the rack that you see that spans between three units, and that piping is brought over to the steam turbine building. You can also see the output from each of the generators going into a transformer. That's right next to where I pointed out the air intake. There is what look like a series of pipes that come out of the combustion turbine, and they're going into an area that has a wall around it. That's where the transformer is. Those pipes are actually electrical, what we call a bus duct. So there's a bus duct. Bus, BUS. There's a bus duct, so you have the three generators there, and then there is a similar one over by the steam turbine building. That large building there is the steam turbine building. You can see the cooling tower in the background, the switch yard, and then the compressor station, the compressor house.
Could you describe the space and size requirements for this type of power project? Let's start with the space, that is land, footprint space that's needed for this type of project.
Yeah, so you can see, between each of the combustion turbines and each of the boilers is that there's some space in between there and in and around it in the road area. And generally what you need is you need enough room there in order to erect the equipment. We call it has to be constructible. And so generally what we do is we look at how much space you need in order to put a rather large crane so that it can be picking up portions of the boiler or the combustion turbine or what have you, and placing them, in the proper location. You also have to have that space in order to maintain these things over the life of the unit. The same can be said for the turbine building, and then you normally like to see some separation between, we call this the power block where you have the gas turbines and the boiler and the steam turbine, and you have some space between that and the switch yard. You like to have the separation with the high voltage equipment. And then the cooling tower, or in the case of what we're talking about, an air-cooled condenser, that would be off to the side. So, generally, a facility of this size, I think that was your question, is how many acres do you need? Or?
Yes, for a combined cycle facility of this size, how many acres would you need to develop?
For a 3x1, I would say you probably need, somewhere in the vicinity of, for the power block itself, 20, 30 acres, depending. Adding in the cooling tower and the switch yard and all that, then, that could grow to the, 35 to 50 acres. And, there's just a degree of variability in there that would be driven by, the cooling technology, the interconnecting voltage, the topography. There could be a number of factors that go into that.
Your answer mentions the phrase 3x1. What do you mean by that?
Three gas turbines and one steam turbine.
And I presume from that there are alternative configurations. Can you describe how that works? Not for this project, of course, but more generally.
Right, yeah. So, you could configure these in a number of different arrangements. One would be a one-by configuration, one gas turbine, one steam turbine.